Hi, in this video I will explain the concept of molecular dipole moment or molecular polarity. In previous lectures we talked about bond polarity, which is the polarity that results from the electronegativity difference between two bonded elements. So whenever you have two elements that have different electronegativity values, such as carbon and fluorine, or carbon and oxygen, or hydrogen and oxygen, then the bond will be considered as a polar bond because of this electronegativity difference. In this video, I will talk about molecular polarity, which is the polarity of a molecule that consists of multiple bonds. So if a molecule consists of more than one bond, then the overall polarity of the molecule is called molecular polarity. And it's actually the sum of all of the individual dipole moments of bonds in a certain molecule. Bond polarity mainly depends on the electronegativity difference between the bonded elements. However, molecular polarity depends on two factors: bond polarity and molecular geometry. So let's discuss the first scenario, which is a molecule that consists of a nonpolar bond. If a molecule consists of nonpolar bonds only, then in this case the overall polarity of the molecule will be zero, and the molecule will be considered as a nonpolar bond. For example, in the case of C2H6, which is like or any other hydrocarbon, the carbon-carbon bond is a nonpolar bond. The carbon-hydrogen bond is also considered as a nonpolar bond because of the small electronegativity difference between the elements. And that's why overall this molecule is considered as a nonpolar molecule. Why? Because mainly it consists of nonpolar bonds. The second case or scenario is that a molecule which consists of polar and nonpolar bonds. In this case, you have to check the polarity, the molecular geometry of the molecule. And you have to check whether the polarity vectors actually cancel each other or not. If they cancel each other, then the molecule is considered as a nonpolar molecule. If not, then the molecule will be considered as a polar molecule. For example, in CO2, we have two polar bonds, the CO bond on the right side and CO1 on the left side. In this case, the polarity vectors, because of the geometry of the molecule, which is a linear geometry, cancel each other. And that's why overall the CO2 molecule is considered as a nonpolar molecule. Another example is the case of, let's say, BF3 molecule. In BF3, we have three polar boron fluorine bonds. However, the overall polarity of this molecule is zero. Why? Because those two polarity vectors, if you add any of the two polarity vectors, their sum will actually be opposite to the other one. And that's why the overall polarity of the molecule will be zero. This is another example, such as in the case of carbon tetrachloride, CCl4, which consists of four polar carbon-chlorine bonds. Again, in this case, we have four polarity vectors. If I added those two, this is going to be their sum. And if I added those two, this is going to be their sum. Overall, those two polarity vectors cancel each other. And that's why CCl4 is considered as a nonpolar molecule. Whereas, if, let's say, for example, I was asked about the polarity of dichloromethane, which is a compound that consists of two hydrogens and two chlorines, then in this case, the molecule will be considered as a polar molecule. Why? Because I have two polar carbon-chlorine bonds, and this is the resultant or the sum vector, and it is not cancelled by any other one. That's why dichloromethane or CH2Cl2 is considered as a polar molecule. It is very important to note something which may make things a little bit easier, is that whenever your central element is bonded to different elements, not the same element, then in most of the cases the molecule will be considered as a polar molecule. And that's why if all the peripheral elements are the same, then we can say that AX2 molecules, such as in the case of CO2, or AX3 type molecules, such as in the case of BF3, or AX4 molecules, such as in the type of CCl4, are actually considered to be non-polar molecules, because the polarity factors in all these cases will cancel each other. But again, if all the peripheral atoms are the same, if not, then the molecule will be polar. For example, if I was given, for example, this molecule, such as beryllium, which is bonded to chlorine from this side and fluorine from this side. Well, yes, we have two polarity factors that are opposite to each other, but again, since fluorine has more electronegativity than chlorine, then the value of this polarity bond or dipole moment will be different than this one. And that's why overall they don't cancel each other. So if the peripheral elements were the same, then we can make this generalized assumption that this type of molecules will be actually nonpolar. Whereas AX2E2 molecules, such as in the case of H2O, the polarity factors will not cancel each other, and that's why this is a polar molecule. Or in the case of AX3E, such as ammonia, or let's say NCl3, where we have three polar bonds. Again, they don't cancel each other, so this is considered as a polar molecule. This is, again, just a general simplification of the concept of molecular polarity. Of course, in more complicated cases, then we have to really check the structure carefully to see if the bonds actually, or the dipole moments, cancel each other or not.